Imagine a world where AI doesn't just predict the next word in a sentence, but understands the physics of a falling glass, the chemistry of a flame, or the way a star collapses under its own gravity. This isn't science fiction. It's the frontier of physics-informed AI, where machine learning isn't just trained on data, but baked with the laws of nature itself. We've seen AI generate stunning images, write essays, even compose music. But when it comes to modeling real-world systems, weather patterns, fluid dynamics, quantum interactions, traditional AI often stumbles. Why? Because it learns patterns from data, but it doesn't understand the underlying principles. It can mimic, but it can't reason. Enter physics-informed neural networks, PINNs. These aren't just regular neural networks. They're neural networks that are trained not only on observed data, but also on the mathematical equations that govern physical systems. Differential equations like Navier-Stokes for fluids, Maxwell's equations for electromagnetism, or Schrödinger's equation for quantum mechanics. Here's how it works. A neural network learns to approximate a solution to a partial differential equation, PDE, say the heat equation. Instead of just fitting to temperature measurements, the network is penalized not just for deviating from data, but for violating the equation itself. The loss function becomes a combination of two terms, one measuring how well the network matches known data points, and another measuring how well the network satisfies the PDE. Mathematically, if we're solving a PDE like delta u slash delta t equals alpha 2u, the network learns a function u, xt, such that the residual r, xt, equals delta u slash delta t, alpha 2u is minimized, not just at data points, but across the entire domain. This residual is computed using automatic differentiation. The network's gradients are calculated layer by layer, and those gradients are plugged back into the PDE to check consistency. This is where the real power lies. Because the network now knows the physics, it doesn't just interpolate between known points, it extrapolates in a physically consistent way. If you give it a simulation of airflow around a wing with sparse sensor data, it can fill in the gaps with solutions that obey conservation of mass and momentum, even in regions where no data exists. But it's not just about accuracy. It's about data efficiency. Traditional deep learning models need massive datasets, millions of labeled examples. In many scientific domains, astrophysics, materials science, climate modeling, collecting such data is prohibitively expensive or impossible. PINNs change that. With just a few scattered measurements and the governing equations, they can reconstruct full spatiotemporal dynamics. And here's where it gets even more elegant. PINNs can handle inverse problems. Suppose you don't know the thermal conductivity of a material. You have some temperature measurements over time. A PINN can learn both the solution and the unknown parameters, like alpha in the heat equation, by minimizing the residual of the PDE and the data misfits simultaneously. This is called a parameter identification task, and it's revolutionizing how we calibrate models in real-world systems. But PINNs aren't without challenges. The optimization landscape is notoriously difficult. The loss function can have many local minima, and the balance between data fidelity and physics compliance is delicate. Too much weight on the physics term, and the network ignores data. Too much on data, and it violates the laws of nature. Researchers have developed adaptive weighting schemes, multi-stage training, and even hybrid architectures, like coupling PINNs with traditional numerical solvers, to stabilize training. Beyond PINNs, the field has evolved into broader frameworks, deep RITS methods, which turn PDEs into variational problems and minimize energy functionals, physics-informed graph neural networks for systems with complex topologies, and even quantum-inspired PINNs that embed quantum mechanics directly into the network structure. One of the most exciting developments, physics-informed models are now being used in real-time control systems. In aerospace, they're enabling real-time turbulence prediction for adaptive wing control. In medicine, they're simulating blood flow in patient-specific arteries with minimal MRI data. In climate science, they're accelerating Earth system models by replacing computationally expensive components with fast, physics-aware neural networks. The future isn't just AI that learns from data, it's AI that understands the universe. By embedding the laws of physics directly into the learning process, we're building models that generalize better, require less data, and can reason about systems in ways that purely data-driven models never could. This isn't a replacement for traditional simulation. It's a powerful complement. When combined with high-fidelity solvers, PINNs can act as surrogates, fast, accurate approximations that allow for rapid exploration of design spaces, uncertainty quantification, and real-time decision-making. So the next time you hear about AI generating art or writing code, remember, the most transformative applications are happening behind the scenes in the quiet revolution of physics-aware intelligence. Not just learning what happens, but why it happens. And that's not just the future of AI. That's the future of science itself.